if you joined us on Tuesday, you might know that we have the answer to our Tuesday teaser question. Jack, can you put it up on screen? So Tuesday, we asked, which laboratory is creating the world's most powerful high-energy neutrino beam? Is it A, CERN, B, Fermilab, C, SURF, or D, NASA? We're now ready to reveal the correct answer, which is B, Fermilab. If you got it right, congratulations. And if you didn't, no worries. We have many more where that came from. We're about to get the show started, so Jack, roll that jingle.
Greetings from CERN, the largest laboratory of particle physics in the world. I'm Chetna Krishna, a science writer at CERN and the organizer of today's multi-laboratory live stream. Today, we are hosting our first ever physics-themed game show, Particle Pursuit. We are very excited to bring this to you together with 3 laboratories, CERN, Fermilab, and SURF. In this game show, you will be asked a total of 11 questions and 4 bonus video questions, which, by the way, some of you guys submitted to us earlier. You can drop your answers in the chat as option A, B, C, or D. The live is being streamed on multiple social media platforms, so you can also take this opportunity to ask us your questions in the chat, and our experts will answer them to you also in a Q&A towards the end. So with that, I'm glad to hand it over to our Particle Pursuit host, Sarah Charlie.
Thanks, Chetna, and welcome back to Particle Pursuit. Today, I'm here at the CERN neutrino platform, where scientists and engineers are building and testing prototypes for a new experiment called DUNE. Today's quiz will be divided into 3 sections: the basics, the science, and the engineering. We'll have a laboratory tackling each section, so let's go ahead and quickly introduce them. So all the way in Batavia, Illinois, we have our friends at the Fermi National Accelerator Laboratory, America's premier particle physics lab. At Fermilab, we have physicist Louise Suter, who will be answering questions about the science of DUNE. Hey, Louise, can you hear us?
Hi, Sarah.
Hey, and where are you connecting from today?
Today, I'm in the neutrino control room here at Fermilab, Batavia, Illinois. Behind us, you can see our shifters recording live neutrino events just at the moment.
Wow, and I heard it's a very special day at Fermilab today.
It is. It's our birthday.
It's your birthday, June 15th, Fermilab's birthday. How old are you today?
We're going to be 56 years old.
56 years old. 56 years old and still looking good and going strong. All right, so now let's head over to South Dakota, where we have the Sanford Underground Research Facilities, one of the few dedicated underground physics labs. There we will be joined by Marcus Horn and engineer Colton Clark. Hey, Marcus and Colton, can you hear us?
Yes, hello, hi. I'm Marcus, this is Colton. Hello.
Can you tell us where you're connecting from?
We are here at the Ross Hoist Room, just above our laboratory in Leeds, South Dakota.
Awesome. So we'll be coming back to them later for the engineering section. And finally, with me here today at CERN, we are joined by physicist Laura Munteano, who will be tackling the basics.
Hi everyone, I'm Laura. I'm a physicist at CERN, and I'm very excited to tell you more about neutrinos today.
And before we give our audience our first question, I guess I should mention there's actually a prize today. Laura, do you know what it is?
I have no idea, but I'm very intrigued.
So today's grand prize will be more knowledge, because isn't having more knowledge really the best prize of all? Okay, anyway, so let's go ahead and get started. Jack, can you put our first question up on the screen? So today's quiz is about DUNE. But what does the acronym DUNE stand for? Is it A, decoding unexplained nuclear enigma? Is it B, Deep Underground Neutrino Experiment? Is it C, dark matter unveiling nebula exploration? Or is it D, deserted and uncharted nomad exoplanet? Put your answers in the chat. All right, and that is time. So Laura, what is the correct answer?
The correct answer is B, the Deep Underground Neutrino Experiment. DUNE is an international experiment with physicists from more than 30 countries, and it will have 2 detectors at 2 locations, at Fermilab and at SURF, and it will try to uncover some of the secrets of very mysterious particles known as neutrinos.
So let's go ahead and watch a quick introductory video about DUNE. Pay attention, because it might help you on later in the quiz. Jack, can you roll the clip? All right, and we have actually another question about the name DUNE. Jack, can you put our second question up on the screen? Who came up with the acronym DUNE? Was it A, Even Bananas host Kirsty Duffy? Was it B, Fermilab director Leah Merminga? Was it C, author Frank Herbert? Or was it D, Sarah Charlie? Put your answers in the chat. And the correct answer is, I get to answer this one because the correct answer is D, Sarah Charlie. So 9 years ago, back when I was a wee bitty little intern about yay high, my boss at the time, the head of communication at Fermilab, sent around an email asking for a new name for a long baseline neutrino experiment, and DUNE was my submission. The collaboration voted on it, and here we are today. So, all right, enough about that. We've been talking about neutrinos, but I'm guessing that not everybody here knows what a neutrino is, which brings us to our next question. As the name suggests, DUNE will study neutrinos. But what actually is a neutrino? Is it A, a ghost-like fundamental particle? Is it B, a heavy boson responsible for mass? Is it C, an extremely dense stellar remnant? Or is it D, a hadron consisting of 2 down quarks and 2 up quarks? If you're playing along at home, put your answers in the chat. And time is up. Okay, Laura, what's the correct answer?
The correct answer is A ghost-like fundamental particle, not to be confused with a neutron, which is answer D, a neutron star, which is C, and the Higgs boson, which is B. So neutrinos are everywhere around us. They come from many different sources, natural and man-made. They come from the sun, the earth, the atmosphere, and even from some of your favorite fruits and vegetables like bananas or pumpkins. So in reality, we're actually bathing in a sea of neutrinos almost constantly, but you probably will never notice them.
So just like all the time, neutrinos are passing through me.
Exactly.
Okay, that actually is a great transition because it brings us to our next quiz question. Every second, how many neutrinos are passing through your body? Is it A, roughly 14 and a half, B, a few thousand, C, around 5 million, or D, more than a trillion? Plug your answers in the chat. And time's up. Okay, Laura, what is the correct answer?
The correct answer is D. It's more than a trillion, and it's actually many more than just a trillion. In fact, you'll interact with very few neutrinos during your entire life. We sometimes say that a person can interact on average with 1 neutrino from the sun during their entire lifetime. And to stop that neutrino from the sun, you'd need about a light year of lead to get it to interact. But the fact that neutrinos rarely interact with matter doesn't mean that we can't detect them and study their properties. In fact, we can make neutrinos ourselves, not only in nuclear reactors, but we can also make neutrino beams.
So like when you say a neutrino beam, I'm imagining like the beam from the Starship Enterprise. Is it a little bit like that?
A neutrino beam is a bit more like a sunbeam. It's like a very bright neutrino flashlight. It's not the easiest particle to make in a lab, but we've been mastering the technique over the last 50 years. And in fact, that's one of the things that we're going to be doing for DUNE.
All right, so if you have made it this far in the program, then congratulations, because we have a prize for you. Caitlin, can you tell us what our audience has just won?
For those playing along at home, you've just won a virtual trip to Fermilab. Nestled amidst the scenic beauty of Batavia, Illinois is Fermilab, America's premier particle physics laboratory and the host of the DUNE experiment. At Fermilab, you can immerse yourself in the captivating world of particle physics while also indulging in the natural wonders of the lab's sprawling prairie land. Preparations for DUNE are in full swing at Fermilab, encompassing everything from testing detector technologies to the development of the world's most intense high-energy neutrino beam. And DUNE isn't the only experiment at Fermilab hoping to unravel the secrets of the neutrino. Several other experiments aim to increase our knowledge of these strange particles and find out whether there might even be a new type of neutrino. Plus, there's more than neutrino physics to explore. Researchers from around the world work with Fermilab to tackle the mysteries of the muon, dive into the strange world of quantum information science, take accelerator technology to the next level, scour the skies for dark matter and dark energy, and search for new subatomic phenomena. Fermilab, where particle beams meet science dreams.
All right, thank you so much for that, Caitlin. We are now ready to go into our next section, the science of DUNE. Here's your first question. What big fundamental question does DUNE hope to answer? Is it A, why matter went out over antimatter after the Big Bang? Is it B, why the expansion of the universe is accelerating? Is it C, why the Higgs boson is so light? Or is it D, what's inside a black hole? Take a little bit of time to think about it. It's quite difficult, this one. All right, so for the answer to this question, we're going to bring back Louise Suter at Fermilab. So Louise, what is the correct answer?
The correct answer is A, why matter won over antimatter in the Big Bang.
Can you explain a little bit more?
Of course. So you can think of the Big Bang like this giant explosion. And in that, we created equal amounts of matter and antimatter. And antimatter, you can think of the opposite of matter, like its mirror image. So when the two of them meet, they annihilate and nothing's left. But you know that in the everything that we have, me, you, table, is all made out of matter. There isn't any antimatter. So this is one of the big mysteries we have in physics is is everything made out of matter? And we're trying to hope that we can understand this question a little bit more with the DUNE experiment. With DUNE, we can make beams of matter neutrinos and beams of antimatter neutrinos, and we can study their properties and see whether or not this will get us to probe a little bit more about whether or not neutrinos can help us answer this really fundamental question about where did all the antimatter go?
So tiny little itty bitty particles with potentially massive implications. Literally massive implications because everything is mass and there's almost no antimatter left in the universe. All right, so now we have our first video bonus question. Jack, can you roll the clip?
Hey, I keep trying to send neutrinos to my cousin at surf, but they keep changing.
Very strange indeed. If I saw that correctly, it looked like she started with an apple and caught an orange. So, Louise, what was happening to those neutrinos?
Those neutrinos are actually oscillating. So neutrinos come in three types, three flavors: electron, muon, and tau. And one of the strange things about neutrinos is they're actually a combination of all of these three flavors at the same time. And as they travel, they'll change which one of those you will actually see, which one you'll observe. You can think of it like eating a fruit cocktail while blindfolded. Your first step is an orange, your second step's a banana, your third step's an apple. And this behavior is one of the things we want to try and measure with DUNE. We're going to place the detector exactly so the neutrinos that we start off with, which are in one flavor called muon, have maximally changed into another flavor, and then we can measure how that oscillation has behaved.
So, Louise, I have a very important question for you. What is your favorite flavor of neutrino?
It's banana. Definitely banana.
My favorite flavor of neutrino is banana too, but you have to be careful because if you eat it too slowly, it might turn into an orange halfway down, and then if your tummy's feeling a little bit upset, that's no good. So we've been talking about neutrinos, and obviously neutrinos are very strange, but something that is also very strange is the experimental setup from DUNE. If you remember from the introductory video, we have two detectors that are 800 miles apart, which brings us to our next question. Why does DUNE need a near detector and a far detector? Is it A, to map the trajectory of the neutrinos? Is it B, to measure the before and after flavor? Is it C, to increase the odds of catching them? Or is it D, to know the number of neutrinos? Please plug your answers into the chat. And time is up. Okay, Louise, what is the correct answer?
The correct answer is D, to know the number of neutrinos. Neutrinos are very tiny, and it's very hard to predict what they will do. So in order to know how many we're going to see in our far detector, we put a detector very close to where we produce the neutrinos, and then we can measure very precisely how many we've made and how they interact. As you remember, these neutrinos are going to change. So when we produce the neutrinos, they're all going to be in one flavor, muon. As they change to the far detector, they'll be something else. So having that near detector allows us to know very precisely how many we started off with, so we know how to compare what we'll see in the far detector.
All right, thank you so much, Louise. So as we know, neutrinos come from many sources, and DUNE will be able to see most of them, which brings us to our first user-submitted video question. Jack, can you play our first social media question?
Hello. My question is, how does the DUNE detector tell the difference between cosmic neutrinos and those produced by the accelerators at Fermilab? Thank you.
All right, how does DUNE tell the difference between cosmic neutrinos and those produced at the accelerators at Fermilab? So, Louise, how does DUNE do this?
That's a really great question. So most of the neutrinos which will actually pass through the DUNE detector are going to be cosmic neutrinos. They'll be neutrinos from the sun. A lot of those low energy cosmic neutrinos we won't see, but we will see the higher energy neutrinos from the sun, and we'll see neutrinos from supernova. This is actually super exciting because it means we're not just a neutrino experiment, but also an astronomy experiment. For the supernova, it's extra cool because gas neutrinos, as we've heard, don't interact. When there is a supernova nearby, the neutrinos will go straight out and come straight to us, and we'll see them straight away in June, whereas the light will get caught up and bounce around. So we'll actually see the neutrinos before the astronomers will be able to see the light that'll get to the planet. So we can tell them where to point their telescopes, and they'll make sure they don't miss it. As for how we tell the difference between the beam neutrinos, the accelerated neutrinos, and the cosmic neutrinos, we use the properties of how we know that we made the beam neutrinos. We know precisely what energy we've made and what direction they're going in, which we can help separate out the signals from the cosmic neutrinos, which will be coming from all directions and have different signatures, and the accelerated neutrinos. In addition, we know exactly what time the accelerated neutrinos are sent. We send a pulse every second, just a fraction of a second long. So we know exactly what time those will be in, and things which are not in time with those we'll know is coming from a cosmic source.
All right, thank you so much, Louise. And for those playing along at home, if you have made it this far in the program, that means we have another prize. Aaron, what have our viewers just won?
Hold on to your hard hats as we take you on a virtual tour of Sanford Underground Research Facility. Surrounded by the majestic Black Hills and rich history of Leeds, South Dakota is SURF, the deepest underground research facility in the United States. Once the largest gold mine in North America, SURF has been transformed into a home for cutting-edge scientific research. From characterizing the geology of rock, to studying extremophiles, to mining for neutrinos and dark matter, scientists at SURF aren't afraid to get their hands dirty, which is critical when building an experiment as massive as DUNE 1.5 kilometers underground. 4 detectors, each one almost 6 stories tall and as long as a football field, will be built underground. And assembling each detector will be like constructing a ship in a bottle from inside the bottle. But first, around 800,000 tons of rock needs to be excavated from the site to make room for these massive detectors. Crews are currently hard at work removing the rock, with excavation already 67% complete. SURF, where researchers dig deep into the mysteries of the universe.
All right, thank you so much for that, Aaron. We are now about to enter our final section of Particle Pursuit, experimental setup and engineering. Here's your first question for this section. Why do scientists do this kind of research underground? Is it A, shielding from cosmic rays? B, it's a stable and quiet environment for sensitive measurements? Is it C, the detectors are so big that there's just not enough space for them above ground? Or is it D, protection from sandstorms, tornadoes, and other severe weather? Please plug your answers in the chat. All right, for this answer, we're going to go back to SURF in South Dakota and welcome back physicist Marcus Horn. So Marcus, what is the correct answer?
Hi, the correct answer is A, shielding from cosmic rays. So cosmic rays are particles hitting the upper atmosphere, producing showers of particles. One of them, for example, the muon, we have like thousands of them hitting us on the surface every minute. If we go deep underground, that is reduced to just 2 or 3 per month.
All right, thank you so much, Marcus. So Fermilab is going to be sending a beam of neutrinos from kind of around outside Chicago all the way to South Dakota. That's going to be 800 miles or around 1,300 kilometers. Which brings us to our next question. How do the neutrinos actually travel from Fermilab to SURF? Is it A, through a tunnel? Is it B, quantum tunneling? Is it C, through the Earth? Or is it D, with the Holtzman effect? Please put your answers in the chat. Okay, time is up. All right, so Marcus, What is the correct answer?
The correct answer is C, through the Earth. We heard earlier neutrinos are not really stopped by a light year of lead. So, you know, the 800 miles of rock and through the Earth is not really stopping them. And that's also the reason why we need these really large detectors to actually capture a few of these neutrinos eventually down here at the lab.
So we've mentioned that DUNE will live in a cavern about 1 mile, 1.5 kilometers underground. But why is this cavern here? That brings us to our next question. What was the surf cavern before it was a physics lab? Was it A, a gold mine, B, an old military bunker, C, a ferment CH, or D, a naturally occurring cave system? Put your answers in the chat. Time is up. Okay, so let's welcome back engineer Colton Clark. So Colton, what is the correct answer?
The correct answer is A. Before SURF was a physics lab, it was one of the largest underground gold mines in the world. And so when the price of gold dropped too low, they shut it down and it became a physics lab. But it also has a history of doing physics. Prior to the DUNE experiment, there was a neutrino experiment back in the 60s that took place while they were mining gold. And so we do have a deep history of doing physics.
Deep history of doing physics, deep underground. So DUNE isn't the first physics experiment that will be built underground, but it is one of the most complicated. Which brings us to our next question. What is the most challenging part of building DUNE underground? A, it's dark, dusty, and dirty. B, the cavern is prone to flooding. C, there's no Wi-Fi or cell service. Or D, logistics. Please put your answers in the chat. And time's up. Okay, Colton, what is the correct answer?
The correct answer is D, logistics. It's extremely complicated getting things a mile underground. The devices we use to get them down there are not very big, and so everything has to be broken down into lots of smaller pieces and reassembled, like Aaron mentioned, building a ship in a bottle in a bottle.
A ship in a bottle in a bottle. So as we know, you're standing in the hoist room, and that is where they run the cables to actually lower stuff into the cavern. This brings us to our next question. How long does it take to bring people and equipment 1 mile underground? Is it A, 3 minutes, B, 12 minutes, C, 30 minutes, or D, over 1 hour? Please put your answers in the chat. All right, Colton, what is the correct answer?
The correct answer is B, 12 minutes. So currently it takes 12 minutes to go from the surface down to what we call the 3850 or 4850 level, which is approximately a mile underground or 1.5 kilometers. But during the homestake days, when they were an operating gold mine, it took a little under 3 minutes to get people underground. Back then, the conveyances moved a lot faster. Since then, we have some aging infrastructure that we're currently in the process of improving. So right now, it takes 12 minutes.
All right, thank you so much, Colton. And now we have another video question submitted from a fan. Jack, can you roll our video question?
At the DUNE project, what steps are taken to address environmental factors in order to ensure precise measurements?
All right, so what steps are taken to address environmental factors to ensure precise measurements? Colton, you want to tackle this one for us?
Yeah, so one of the things about where the DUNE experiment is being built, where the detectors are, is a very stable environment. Temperatures are very consistent, the humidity is very consistent, and what isn't consistent, we control everything. We control the temperature, humidity, ventilation, that's all controlled here at SURF. And so we have very stable conditions underground.
All right, thank you so much, Colton. And we actually have another video question from social media. Jack, can you play the other question?
How much does a neutrino weigh?
How much does a neutrino weigh? Very good question for that. Let's welcome back Laura. So Laura, how much does a neutrino weigh?
So someone's been paying attention. That is an excellent question because the answer is we don't actually know. What we do know about neutrinos is they have some amount of mass, which is very small, and that's necessary because otherwise they wouldn't be able to oscillate or to change their flavors, as you've seen earlier. However, we don't know the exact scale or the size of their masses, but we do know the upper limit of those masses. So we know how heavy, the limit to how heavy they can be. We don't actually even know what types of neutrinos are heavier than others, but what we do know is that they are so much smaller and so much lighter compared to other fundamental particles that this is really puzzling. So for instance, if you compared the mass of a neutrino with the mass of the other fundamental particles in our theory of fundamental interactions, the standard model, then they would be as light as a bug is compared to a skyscraper.
A little tiny bug, like a little ladybug in the Chrysler building?
Yes, pretty much.
That is enormous.
Yes.
All right, so we have reached the end of our 11 questions, and we are about to go to answering your questions from social media. But first, isn't anybody curious what this experiment will actually look like? Well, luckily, right behind me, we have 2 prototypes for DUNE. They're about 1/10 the size of the final detectors. And my colleague, Chetna, was lucky enough to get a tour inside. Jack, can you roll the clip?
So, Emmanuel, where are we right now?
Right now we are inside of ProtoDune. That is one of the prototypes for the DUNE experiment. That is a long baseline neutrino experiment that will be built in America.
How big is this prototype?
This prototype is pretty big. In fact, it's one of the biggest prototypes ever built for an experiment. It measures around 10 meters of height times 10 meters of side for the base. And it hosts up to around 1 kiloton of liquid argon.
And how big would the actual DUNE experiment be?
So DUNE will consist in 4 modules, and each one of those modules will be more than 20 times the size of this prototype. So it will be, yeah, pretty big. Inside of DUNE, we have in the middle of the chamber a cathode that reaches a very high electric potential, so that inside the chamber we have electric field on both sides. At the top of the chamber, near the roof, and at the bottom, we have instead an anode, where the particles are collected as a consequence of their motion inside of the cryostat due to the electric field.
And this room would be filled with liquid argon. Why exactly?
Yes, so liquid argon is a kind of technology that was already tested in other experiments such as Icarus, and it is very good for the higher probability of neutrino interactions in respect to other kind of materials. Also, argon is an interesting element because it produces both ionization, so separation of electrons from the nuclei, and light when this happens. So you can detect both the electrons that come from it and the light. And combining this information, you can have a very clear image of what happened inside of the detector.
All right, and welcome back. So our first question is actually a question that I have. So I'm still really puzzling over this whole neutrino oscillation thing. Do other particles do this weird thing that neutrinos do?
Yes, neutrinos are not the first particles that we've known to oscillate. Actually, quarks also undergo this phenomenon. So they can change from one type of quark to the other. And a lot of the maths that we use to describe quark oscillations or quark mixing is very similar to the one that we use for neutrino oscillations. However, what we do know is that the way in which quarks oscillate could have potentially maybe offered some explanation about the matter-antimatter asymmetry puzzle, but it seems that there's not enough of this amount of mixing in quarks that could explain everything that we see today. So we're hoping that neutrinos can maybe give us a better answer about that.
So a lot hinging on neutrinos. Okay, so we have a question from John that was submitted on Fermilab's social media. So John asked, given the source and target are a constant, will the neutrinos all be the same flavor? I think this is a good question to send over to Louise. So Louise, will all the neutrinos be the same flavor when they arrive at the FAR detector?
So as the source and the target are constant, the neutrinos that we produce will all be the same. We produce neutrinos in the muon flavor. But as those muon neutrinos travel, they will oscillate and become different flavors. There'll be a combination of tau, electron, and muon neutrinos when they get to the FAR detector. And it's those ratios of the different types is one of the fundamental things we're trying to measure with DUNE.
All right, thank you so much for that, Louise. So we have another question from the audience. Jack, can you put it up on the screen? So we have the question, we only see a tiny percentage of what we think is out there because of the fact that neutrinos don't interact with matter often. Do we have a good approximation of that? So a good approximation of the total number of neutrinos, I'm guessing? So who wants to tackle this question? Laura, how you feeling today?
Well, I don't know the exact number of neutrinos that we have in the universe. I just know there's many of them. What we do know is that the probability of a neutrino interacting, especially at the energies at which they usually cross us, is many tens of orders of magnitudes smaller than those of other fundamental particles.
Awesome, thanks, Laura. Louise, do you have anything else to add? How do we know the total number of neutrinos in the universe?
The total number of neutrinos in the universe is a complicated question. You know, we have some calculations from the Big Bang about how many were produced. Those big neutrinos are actually a large number of the total number of neutrinos in the universe. Plus, we know we can calculate quite precisely neutrinos which are produced from suns. And we know precisely how many we've made from the beam. But that is a complicated question. I don't think I can definitely can't give you a number off the top of my head of the total number of neutrinos. Many.
All right, and now we have a question for Surf. What has been the most exciting part of the DUNE journey so far? Oh, we can't hear you.
All right.
We hear you now.
All right. What I wanted to say is the most exciting part is actually seeing the caverns being excavated underground. We walk by there every day and have a glimpse into these caverns just from the side safely. And you see them growing every day and they are ginormous, simply ginormous.
All right, thank you so much. I have another question for Surf. So Surf has dark matter experiments. If you've been following physics, dark matter is this unseen, probably particle that only interacts gravitationally. Seems like neutrinos are also these little teeny tiny particles that don't really like to interact very much. So how do we know that dark matter is not just a whole bunch of neutrinos?
Well, that's a good question. The neutrino is actually, in some way, a dark matter particle candidate, but it's just too light to actually make up all the dark matter that we are needing in the universe to explain this phenomenon of dark matter itself. So the neutrinos are just too light. They would wash out in the early universe, and you wouldn't have these large structure formations that we actually see in the universe. So unfortunately, it's not the best candidate. So we are also looking for other candidates.
All right, thank you so much, Marcus. We have another question, very good one. Can neutrinos be their own antiparticle? So I think this would be a good one for Louise. Louise, you want to tackle this one?
Yes, neutrinos can definitely be their own antiparticle. That's something that we don't know and we're trying to investigate. And there are various theories that suggest that they will be. So yeah, that's one of the big mysteries about neutrinos, that we're still trying to learn about them.
Okay, here's another. So we have our very last question. It is, so we have a beam of neutrinos. Will the neutrino beam have an effect on other experiments at SURF? That's actually a really good question. Let's send that over to SURF. So SURF, what effect will Fermilab's neutrino beam have on your other subterranean experiments?
Well, actually not a lot of effects. As we learned, the neutrinos are not really interacting a lot, so our other experiments will just not see that many neutrinos. And even if we would be able to see those, you could just kind of like assume them as a background, like all the other backgrounds that we are facing. And we also know when the neutrinos are coming, where they are coming from, and what energy they are. So they are well understood.
All right, thank you for that, Marcus. And with that, we have come to the end of Particle Pursuit. So I'd like to give a big thank you to Fermilab and SURF for joining us today. This has been a whole lot of fun. I hope you watching at home also had fun, and we will see you next time.